Hi, this is Robert Bolaños. Welcome to the analysis and design of a flyback. This is video 26. How to verify the model. Okay, before I go on, if you find the video informative and you like, please subscribe, like, and share. Okay, so I got that out of the way, so I'll go ahead and continue. Okay, so far we what I developed or what I showed is how to develop an average model. Okay, and the average model that I'm using is Jax Alexander model. He's my mentor that taught me this model. Okay, so I'm just passing information that he developed a long time ago. Okay, and then second, I showed I believe in video 24 how to plot the response of the output filter, the opto, and I believe even the error amp, and then the total. Okay, so this should be something that hopefully you're picking up as your simulation setup tools, I guess you can say. And then lastly, I showed how to do the loop response. That's the response that looked kind of like this. And then I had the phase come in like this. And then showed that where it crosses, that was the phase margin, and where it crosses here and you look down here, that's the gain margin, so forth. So this is what you're looking for. You want the total loop response. Okay, so that's where we're designing. Now I didn't specify what is bare minimum, so the phase margin the absolute minimum industry standard, this is a number that I've seen, but this would probably be a more conservative and better 60 degrees. Anything above 60 degrees is probably good enough. Okay, and the gain margin is negative 10 dB. So you have greater than 10 dB, you're doing good. Okay, so now that you have these skills, okay, how do we have confidence that the model, and let me show the model. Okay, this is the model. Okay, this is an average model, and this is the switching model. Totally different. See, here you have the switch that simulates a MOSFET. You have your transformer. This is a UC 1843. Okay, and if you notice, this is a switching model. It takes a long time to simulate. Okay, and the switching model, excuse me, is used to calculate the voltage and currents. Okay. Now the average model, it's got two specific things. Usually it's used to see what the loop is, and if you notice, there's no transformers. The transformer, the MOSFET and everything is modeled just by a voltage control current source. Okay, that's the jack model, but everything else is the same. Okay, so this is what we're trying to validate. How do we know that this is equal to that? Okay, so that's what this video is supposed to do. Okay, so how do we do that? Okay, so what we do is okay, we're using the average model, and we're performing a AC analysis. Okay, but you can also do a transient analysis. Transient would be similar to a scope, an oscilloscope. AC model would be like a spectrum analyzer or a Bode plot. Okay, so the average model we use mostly for AC analysis, but we're going to do a transient analysis, and then we're going to use the switching model. Okay, we're going to use the model. Now on the switching model, you cannot do AC analysis. You can only do transient. So then we're going to compare these two, the results of these two. Okay, so we're doing the switching model, we're going to do a transient, and we're going to use the average model. Remember, we want to see whether these are equivalent. Okay, and the way we're going to test is we're going to do a transient. So hopefully that makes sense. Okay, so when we do the transient, we're going to do, let me go ahead and capitalize this. We're going to do a dynamic loading. Okay, so what does dynamic loading means? Okay, well, we're going to vary the load. Okay, so this is our model, or it could be a power supply. Actually, you can do this with an actual power supply. We test, we regularly perform dynamic loading tests on power supplies. We use an electronic load where we can switch from one current to another. Now, in this case, this is a 12-volt supply that we designed, and we designed it for half an amp. Okay, so what we're going to do is we're going to go ahead and switch it from half an amp to a quarter an amp. So one way of doing it is by putting a resistor, a 50 ohm, and this will give you 0.25 amps. Okay, and then we put another resistor and kind of in parallel, but with a switch. Okay, and when we switch, then we have two in parallel. So then we're going to have 250 milliamps and 250 milliamps. That should be this. And when this is open, then we'll have 250. So we should have a waveform that looks something similar to this. It goes from from 0.5 amps, and then when the switch opens, you only have one resistor. Here we have two resistors. Okay, so basically you're going to go from half an amp to a quarter an amp, and then half an amp again. So now what we're going to do is we're going to monitor the output, and this should be the output. Okay, this should be 12 volts. Okay, so when you're demanding, or you have both resistors, you're going to be pulling half an amp, but then as you go from half an amp to a quarter an amp, then you have less of a load, so this will go up. You're going to see a positive spike. And then as you go through the transition in time, and then you demand it or you tell it to go from a quarter an amp to a half an amp, then you're going to have a droop. Okay, so this little droop, how much it deflects, and then the time constant, in other words, the time that it recovers, is proportional. Let me redo that. They're proportional to the loop response. Okay, so let me give you a little bit of an example. So let's say this is the loop response. And let's say that the crossover frequency is 1 kilohertz. Okay. And let's pretend that this is the loop response for 1 kilohertz. But let's say you move the loop response back here to 10 hertz. So if you have a crossover at 10 hertz, then this is a much slower response. So then you'll end up having something that looks like this. Since it's much slower, this will have a higher deflection and it'll take longer to recover. Okay, so that's where I'm saying that this is a very good test to show the equivalency. In other words, if we are able to perform this test on both the average model and the switching model, then we have very high level of confidence that they're equivalent. Okay, so let me go ahead and do the simulation. And I'm going to do it a little bit different just because it's the second method of showing this. Okay, so instead of using two resistors, I'm using this switch. This switch, what I'm telling it here is I want it to switch when it's on. Basically, when this voltage turns it on, it's going to be 25 ohms. And if you have 25 ohms, you're going to have half an amp. And then when it turns off, then it should be the equivalent of 50 ohms. So basically, when you're switching on and off, it's going to go from half an amp, quarter an amp, half an amp, quarter an amp. Okay. So I have it set up, and I go. Okay, so here is the output voltage. Let me go ahead and add the current so you can see what I am. There would be the current through my G1. Okay, the current here is 1 amp because it's charging. Capacitors are discharged, so there's a lot of current, but then it settles down once it goes to steady state. So if you notice, it's approximately 480, 482 and 243. Okay, so if you notice, when the current goes down, there's a little up click. Okay, that's what I want to show. So basically, when the current goes down, this goes up, and when the current goes up, it goes down. Okay. Now, mind you, if you notice, let me rerun this. It runs very fast. That's why we use the loop or the average model to do this type of analysis. This very fast. Okay. So now we're going to compare that, and we're going to compare it with the switching model. Okay. Now I went ahead and did the simulation. Problem is, when you do a switching model, it literally takes about a good 15 to 20 minutes to do the simulation. So instead of waiting here, I already have the model here, or the waveform, at least one of them. Here's a waveform. Okay, so now what I'm going to do, and you can tell this is different because if you expand, you can see the ripple. See, that's the actual ripple. Okay, and if you look at the average model, the average model doesn't show the ripple, but this does. Okay, so this is how you can tell this is a switching model. So now what I'm going to do is I'm going to go ahead and open up the file that from the average model. Remember, this is the switching. Now I'm going to import the average data or simulation. Okay, so now I'm going to add V out. If I can find it, there it is. And I'm not sure if you can see it, but you can see a little bit there. So what I can do is I can let me put this under graphic mode. Okay, the data are both being plotted. So let me go ahead and go to trace options, and the V out is normally thinner. I'm gonna go ahead and put it twice so you can stand out. So if you notice, the blue is the switching model, and let me go ahead and now expand. Blue is the switching model. Okay, bang. Notice it's right in the middle. That's why they call it the average model, because it's averaging. It's much faster, and if you notice, it's almost right in the middle. Okay, so this I consider is a good agreement between both models. So this gives me very good confidence that the average model is equivalent, and that when I set my loop, I'm going to have a very high level of confidence that is correct. So again, take a look at it again. That looks real pretty. I mean, it's just I get a kick every time I see this. And that they're actually match up fairly well. So it's always wise that when you do the average model, try to verify it. After a while, you know that once you gain enough experience, you can bypass or not validate it, but because you've done it so long, you have confidence in it. And but it's always good just to check it, make sure that everything works good. So again, let me go ahead and copy this. It's not going to let me copy. Okay. Well, we'll go ahead and stop here. So at least I know, I'm glad that I was able to show that the simulation works, and you'll be able to put it into practice. Hopefully, I guess the next task would be, these are a current mode control. One of the viewers suggested maybe a voltage mode control. That's where you have a double pole, and you would use the type 3. So that might be the next video that I will do. Anyway, if you have any questions and comments, you can email them to my email address, or you can post them here. And like I said, if you have found this video informative, please subscribe, like, and share. Thank you for listening.